So it hasn't been really all for nothing. We have learned some things, right? So, but let's try. Let's keep trying. So I'll start from scratch because it was just too cluttered. So, but we've learned definitely that the actual amplitude amplification um, operation is something that depends on how you create your initial superposition, really. So it's an interesting learning. So, for example, if you would go ahead and you wanna start with like a 0 0 superposition, so with like a now you're like a plus plus plus, and we apply whatever oracle. Ugh, why is it so laggish? Okay, and now, you know, you actually need to apply like so after your bunch of Hadamard's, you need to apply a bunch of X gates first before going for your control Z, because there's no way that you can um, there's no way that you can basically use an amplificator here that is like 0 0 0. There's just no way to construct that because I mean I guess this is the way the circuits are designed. I mean the way the notation is designed, because you could maybe put in like if you could do something like this. Oh, why isn't it? So if you could do something like this and that they would all get connected, then you would not need those X's at all. So I guess this is just a circuit editor limitation, right? Um, but so say you're say you want to use the you want to start with the superposition 0 0 1, right? So then you would need to use these thing here, right? So which is the same as like would be the same as kind of sticking with these, but then putting x's around just those two elements, because you want to match these and these with these here. So we've learned that, so that's good. I mean that's what I kind of. It's not that I don't know if I really mentioned it explicitly, but it I don't know. It kind of felt like that was related somehow to the seat of the superposition, if you want to call it this way. So, um, having said that, so there must be something behind the need to match that. You know what I mean? Um, Now, Craig's more compact version basically says, no, 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 get rid of this, get rid of all the Hadamard's, and instead of using that, use the, in this case, we gotta use and I would probably have to do no, I would probably have to surround that with Zs. No, why? Eh? Oh, sorry. So if I would start with zeros, I would probably have to surround that with Zs. No, or with X. I'm stupid. No, why it doesn't work? Because that is. Oh, sorry, that's a y-axis control. I'm so stupid. This is the one that you should use. And is it X? No, it's Zs. It's Zs because you're exactly. So now that works again, because there's no way, like there's no such like if that would connect, then we would have it. If those three operators would connect, then we would have what we want, 0 0 0, right? So we need a match with a plus plus plus, so to say. That's what we're trying to do, but we can't because that's an x-axis anti-control. Conditions on a qubit being on plus off. Okay, um, so you need to work around this limitation by doing the wrapping that with a z, because it's the equivalent of, it's just to turn the plus to minus and minus to plus, right? That's the idea. And then you see that the oracle 111 is the one we get here flagged. So, but that's why Craig is basically using the following circuit to make it super compact. Starts basically with 111, and then he goes again and says, okay, that is the super compact Grover's algorithm. Yeah. Mm, let's use maybe let's use another. Let's use the 001. So this is the 100. Sorry, 1100. Yeah. And so you would use that Oracle. I should turn that into an Oracle actually. So I should say two. That's my Oracle. Um, so I can use this Oracle. Oh yeah, and I wanted to add basically out of because that was a convenience thing to have. Uh, I will call it this time observe X, and just to make it nice, I would call that also observe Z. So I'm kind of using this. It's the same really, but I'm using it. It's maybe going to be nice to say, okay, switch to observe X, and then you can observe X, and then go back to observe Z, right? So it 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 looks nicer, I think, than having switch X, switch X. So it's like now switch to the X observable, and now switch to the Z observable again. Yeah, that kind of makes sense. Um, Notation wise looks nicer. I should probably save that, those custom gates. So I'm trying to figure out, maybe Oracle is not even needed, but I'm trying to figure out and maybe I can just to make these here, so I can maybe even do like 3 being the amplitude amplification for that particular circuit. So now I even have it more compact, and I can just use that. So I know, okay, so I add amplitude amplification. So now I can basically, you know, keep repeating that, and now it's like the top. If I do this again, I think now it's already gonna exactly sort of cycle back again. And that basically tells me that there's indeed something to do with kind of like sucking in and out these amplitudes. It's kind of like rotating, right? Um, we'll stick to this to just one iteration, because with 3 qubits it's good enough already. Um, oh, where do I start? Where do I start? Maybe I should take a look at density matrices. Maybe that helps me somehow. But they're big. They're definitely big. What if I now go to observe X, put another density matrix, and now I go back to observe Z. Yeah, it sort of matches the amplitudes, I guess. I don't remember whether I got to a conclusion on what those like off diagonal elements are, whether they kind of basically define your correlations. I think it was something like that. They define your correlation. And if I don't think the density matrix is going to help me, honestly. If I do the same after applying the oracle, so I basically copy these, copy these, copy these. So after applying the oracle, I this, this, oh come on, this, So nothing has happened really. How's it possible? It's not visible in here, nothing has happened. But if I do that after applying the amplitude amplification, then I see some kind of correlation in here. That it's a bit stronger. You see that those things have like is 0.06 and this is 0.18. So there seems to be everything kind of correlated with 111. Eh, if that's what it means, really. But let's get rid of this. I don't like it. I don't think it's showing me anything. Oh my god. So what else can I take a look at? What else can I take a look at? Hmm. I don't know really. So I'm gonna cloud again with this place. I'm gonna do the same game again. It's like it's not gonna help me. Mm. Why does the amplitude amplification need to be related? That's a good question. So why does the amplitude amplification need to be related to the seat of this superposition? Maybe maybe I should try to read again the rotation interpretation that Craig maybe that's worth doing. So from Craig's blog, there's the controls, I think. Exactly. Maybe I will read again these. I'll read again these. And then I'll read these. Let's see if we can. So controlled operations are a core part of quantum computation. Not strictly necessary, since any 2-qubit gate tends to be sufficient for universal quantum computation, but certainly common. For example, the core of both Grover's and Shor's algorithms are defined by control operations. Shor's algorithm uses controlled multiplication operation as part of estimating the period of multiplying by a constant mod r, and in the case of Grover's algorithm there is a giant controlled z right in the middle of every step. As a segue into the meat of this post, I want to point out something common to both these examples. The controls are bracketed by Hadamard gates. The bracketing is blatant in Grover's algorithm, that might not have noticed before, and here you have it. And Shor's algorithm is like, okay, between these and the QFT. That's what he says here. This pattern of control surrounded by Hadamard is common enough that it's worth packaging into a single logical thing. I call these an x-axis control. In this post I'll be representing x-axis controls in diagrams with a little circled plus. So basically these. The reason I call this H control H thing an x-axis control is that instead of conditioning operations in the control qubit being in the state 1, an x-axis control conditions operations in the control qubit being in the state minus. And that the state is on the x-axis of the Bloch sphere. This makes sense. The Hadamard operation basically swaps the x and the z axis, so bracketing z control, axis control with Hadamard turns it into an x control, and vice versa. As we'll see in a minute, the x-axis control is associated with the x gate in the same way that a normal control is associated with the z gate. That's pretty neatly explained. Now, you may be thinking, hold on, don't we already use a circle plus to represent x gates? Why are we using the same symbol again? Isn't that confusing? That's fair, but actually it makes a lot of sense to use the same symbol for both, because x-axis controls are often interchangeable with x gates. If you have an x gate controlled by an x-axis control, you can swap them without changing the applied operation. That's actually the same you can do. The same happens with the control z's, right? Um, because I didn't know the fact that diagram above when I added x-axis controls to Quark, I picked the wrong symbol for them. Since the matching state has a minus in it, I figured using a circled minus was most natural and a plus for the inverse control, but the interchangeability with not is much more important, so the next version of Quark, okay, so but that's already fixed. Taking the switch operation, taking this switch operation and control concept be farther, note that the control not is equivalent to a z controlled by x. Yeah. I hope you're starting to get the sense the operations and controls are awfully similar to each other as long as they have the same axis. Exactly. In fact, that's correct. In the same way that every rotation has an axis, every single qubit operation has a corresponding control. We can freely change which qubit is the target of an operation without actually changing that operation, as long as we keep the axis consistent. So basically, these, you can flip that, you can flip that, you can flip that, yeah. This equivalence between operations and controls even works for partial rotations. Interesting. Yeah. I would go so far as to say that the fact that we distinguish between operation and control, at least in the cases diagram above, is just a historical accident. Agreed. A vertical spandrel inherited from classical computing. In the context of quantum computing, it doesn't make sense to call out any of the wires the target of any operation diagrammatically. Taking a hint from a common notation for CZs, we drop the whole target thing and just use a bunch of linked controls. For partial rotations, we can use an outside indicator to show how much to phase. Yeah. Basically, that's a neat notation, basically. Yeah. So basically what we're doing in the above diagrams is describing operations in terms of the eigenvector they affect. Instead of thinking in terms of a specific qubit being turned conditionally, we think in terms of a direction in the Hilbert space being negated or phased. We're thinking in terms of the whole system instead of its parts. And that's kind of, it feels like a crucial way of summarizing this. This perspective of controlled operations as direct specification of how the Hilbert space is of course how to phase Hilbert space is of course a very useful tool for intuition when thinking about quantum circuits. For example, the controls only approach makes Grover's algorithm simpler in two ways. Yeah, that's the it's a really neat, yeah. First, it pushes you to think in terms of the overlap between the solution vector and the diffusion vector, which leads to the elegant rotating towards solution interpretation of what Grover's algorithm is doing. Second, okay, so that's the interpretation that I want to dive into, because it's the one that I basically didn't like in the beginning, but it might just be the one that really makes it for me. I don't know. With all that praise, just in control size backtracking over reasons calling out individual wires as the target is also useful. Okay, but the rest of the article, yeah, that's not I think relevant. That's where I wanted to get right now. So consider the plane spanned by S and W. Plane spanned by S and W. Okay, so we've got S and W. Equivalently, the plane spanned by W and the perpendicular ket S prima. Okay. We will consider the first iteration acting on the initial ket S. Since W is one of the basis vectors in S, the overlap is this. In geometric terms, the angle between S and S prim is given by this. Okay. The operator UW sub W is a reflection at the hyperplane orthogonal to W. That's just too geometrically abstract for me already. For vectors in the plane spanned by S prima and W. It acts as a reflection across S prima. So It's therefore to check that the operator is the curve situation step rotates the state vector by a particular angle. We need to stop when the state vector passes close to W. Okay, so all what this is saying is that's the first step is the reflection, and then you've got the actual amplification. But it's still not clear to me. But that's still far away from being clear to me. So if we just use amplitude displays, here we'll just use 2, and here we'll just use 2. Okay, and this is going to be observe X back to observe Z, observe X back to observe Z. So again, that is my Z observable, that is my Z observable, and that is my X observable, that is my X observable. That makes it easier for me to see graphically. What the hell is happening here? We cannot. Oh my god, no. We can add an amplitude display here, which is. Oh, come on. An amplitude display here, which basically and observe X, observe Z. Exactly. So again, so this is the blue ones are, so blue is Z, and red, or this color is X. So if we read operation by operation, so so I just had to pause for a second now. Had to go to the bathroom. It's just something Craig said here that it's just intriguing me right now. So negate. Negated in terms of a direction in Hilbert space being negated. And I said something in the previous video about these kind of phasing a superposition. Correct? Or at least that's the feeling. Phasing the elements of a superposition that match like that particular direction, like minus minus minus. So in theory, I think we can get for these we can get rid of the X observable thing that's useless if we stick to that view of the thing. If we stick to that construct here, and then what we're seeing in here is that if we take that, right, and we think that what the amplitude amplification is doing is basically negating, it's phasing in the direction of a minus minus minus. And so that would mean, and here you've got like a minus minus minus, and here you've got like that little tweak minus 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 that it has basically that phase flipped. That is the phase that's flipped here. That's the only difference. And that's basically, how can I bridge that step? Because that's intuitively basically why this absorbs the amplitudes. That's what I would intuitively say, but why? Okay, maybe that's like a little step forward in my explanation. let's just say that's roughly correct, right? Intuitively, that you see those amplitude amplifications as kind of negating based on the x-axis direction. So you're still like a minus minus minus. Mm. So if we've got like 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 0 1 1 0 1 1 1, and then we've got like plus minus minus plus 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 minus. So that's kind of the state before. And now saying phasing against the minus 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 direction. So in order to phase, because for this to be minus minus minus, there's just one little difference, which is that these, oh my god, that these should be a minus. That's the kind of only difference. If I flip everything else, the sign of everything else, that doesn't change really anything, right? I mean, it's not that there's any interference, although there seems to be. There definitely seems to be. But why? It's as if there should be something that points to that 1 0 0, or that's getting closer to pointing to that 0 0, to that 1 0 0 for some reason. So So let's put it this way. Each of these combinations uh, each of these parts would explode into their own 8 different possibilities after applying Harman gate. That doesn't make any sense. Oh, but I think I'm there almost. How can I understand that rotation, or how can I bridge that towards this thing of the vector getting close to the solution? What does it mean? The key is probably, what does it mean, the direction in a Hilbert space being negated or phased? And I know I've been thinking about this before, and I know that I think I didn't never like I never moved forward to the fact that it's negating the kind of superposition. Think in terms of the full system, of the whole system. Not far away from this though, not far away. It's just, I feel I'm almost there. Come on, 5 more minutes, come on. So, what does it mean numerically here? What does it mean to rotate the Hilbert space, to rotate it in the direction of minus, minus, minus? What I would imagine is that a minus, minus, minus is what you should flip. But a minus, 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 right, has a minus in here. So, in that case, if you didn't apply an oracle, that's just what it does. But when you apply the oracle, whoopa, when you apply the oracle, it just balances the whole thing. That's what's amazing. You see? Boom. Nothing. Like, the superposition is just flipped. That's the expected behavior of the amplitude amplification occurred in this case. In this case, that's of the x-axis control. But because of the oracle in the middle, then we're creating this interference pattern that makes the amplitude kind of gather towards that difference. If instead of that oracle, we would have an oracle that, for example, just does these, right? So it considers kind of it creates a difference in its proposition that it's more in than in just one spot. It's basically in 110 and 111, right? That's also where the stuff, where everything goes and fills up. And the same if, okay, if you would use just that, then what happens here actually? That's probably an extreme case because we're at 3 qubits, so you at least gotta cover 2 of them. But what, just out of curiosity, what happened here? Nothing happened. That doesn't have any effect. Interesting. Okay, that's something else to explore later on. Let's go. Let's stick back to our original oracle. Let's think let's think backwards in the sense that maybe let's reduce dimensionality even more. Why not? Let's just can we reduce dimensionality even more? We'll just use 1 1 Hadamard's Hadamard's. We will use this oracle. I'm not gonna do all the gates in here now, and I'm gonna use these. Okay, so we got it, and then we now have the density display. No, the amplitudes here, the amplitudes here, and the amplitudes here. So, and basically the same has happened. Let me clear everything. The same has happened here, right? So we've got that like closed open pattern, and here basically this has been flipped. So we've got 0, 0, and 0, 1. Let me clean this up. The reason I reduce dimensionality is because it's going to be easier for me to write these numbers 0, 0, 0, 1, 1, 0, 1, 1, because there's just 4 of them. 0 is a plus, this is a minus, this is a plus, but should be a minus, right? And this is a plus. Now, our minus minus, or 1 1 seated superposition minus minus should really be like this, right? Minus 1 0 plus 1 1. So that's this, and that's this. Now, if we think in terms of what this operator is supposed to do, this guy is supposed to flip the phase of a minus minus. So this. Oh, wait a second. What if we? I mean, that's maybe really stretched out, but I mean, if you think about it, how would you phase that? So you would get that. So you would add plus, like you could think of it this way, right? Correct. So you would basically like add that, and then those things and then these would cancel out with these, and then you would get exactly that mathematically. Okay, so let's imagine that we have that. So this was this minus 1 0, but now we've added plus 1 0 plus 1 0. Sort of, what if we add, what if, let's imagine that this is the outcome of adding, of mathematically speaking, right? This is adding that to our mixture. Let's just assume this is a way to represent that. How would you flip that mathematically? So now, if I apply that and I say, okay, so now I go here and I flip all the signs, now I get a minus 0 0 plus 0 1. This becomes a plus 1 0, and this becomes a minus 1 1. But now we've got, oh my god, I think I got it. But I kind of resorted to some sort of mathematics to artificially define what this means, or to artificially define what the actual oracle is doing. Because it's adding the phase, but it's not just changing the sign, it's just adding or removing stuff at the end of the day. And then and then that operator basically flips that, and then that's why it sucks in the amplitude. That's genius to see. Oh, okay, I need to let that sink in. Let me try to express that again. Oh my god, that may be it. that may be it. So let's try to use colors the right way. We're at this step. So, and I'm going to use this part of the screen. So this is basically plus 0, 0, minus 0, 1, minus 1, 0, plus 1, 1. Now, let's change the color. We execute that operation, which basically what it does is it adds to the mix plus 1, 0, plus 1, 0. So, you do it this way. So if you now observe the system, basically, this cancels out with this, and then you get exactly that, right? So you're getting that. Oh my god. Yeah. I feel awkward because I don't know if that's fine. I don't know if that's right to see it this way. But it just looks trivial this way. And now we're gonna do that, which basically what Craig says is what this does is it flips signs of that that particular direction, which in this case is like a minus minus, which happens to be this part. So what this does is it does minus 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, but you know, because of the interference we've added, oh yeah, so that's basically the effect of the added interference. I mean, it's not that you're adding interference, it's that I mean, in order to interfere, you're just kind of adding or removing things. That's like the shift you're doing, right? And now those things don't cancel up anymore. They just don't cancel up anymore because of the phase shift. They don't cancel anymore. I was all the time thinking that, I was all the time, so, and basically what you end up with is like these three times. So you have, you know, so you have a much more, I don't know, maybe that's not the right, because maybe that's totally good. That's not maybe totally correct, honestly, because here you end up literally with zero and just these, right? And technically, you do have some portion of that in here. I mean, if we would normalize that, it would not give you that, or maybe almost that. I mean, I just made up these, right? I just made it up that it adds plus 10 plus 10, plus 1 0 plus 1 0 just to make the numbers work. But what I'm trying to say is that's where the interference takes effect. Is that you have to think that the interference really is the result. So when you're like your minus minus never disappeared. That's what I want. That's what I want to say. Your minus minus never disappeared. It's there. It just has an added component of noise or whatever, and which is created by these that makes it interfere. You know what it helps is if you think about the fact that these are kind of waves oscillating all the time. So it's not that it's something that just happens and bam, that's it. So it's like if you've got your wave, and then this operation adds something else in here that basically cancels out and cancels out. It's not that it cancels out, but it just creates that dephasing effect. And so then when you're doing another thing, I'm lacking the vocabulary, but I think I got it. It's just the way you think about. That's that's. Oh my! I'm sorry because I probably feel like I'm just bubbling, blah 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 blah. But that's basically, I think a key element of this thought process here is that you're not it's not that you're executing like operations on numbers and that's it. It's that you're adding things into your waves, right? And so the waves are always there, so you never lose that. That's my point. I kind of thought, okay, you flip the sign, done, you've lost your minus minus. It's that it's there in conjunction with something else that's creating that disturbance that then it makes you feel like you've lost the minus minus, but it's you never lost it. So maybe that's an intuitive explanation that it's not much to do with rotation somehow. And so and so that x-axis control basically negates you that, or it faces that, which then flips the effect of the interference. Bam! That's it. The x-axis control here basically flips the effect of your interference back, like uh, towards the opposite way, and that's the, and that's this mirroring. Yeah, and that's this mirroring. That's this here, of course. So that geometric proof of correctness, that geometric version is actually it's what makes sense. It makes sense because you're kind of dephasing, and that basically mirrors your whole thing, because it mirrors the effect that you like the this effect. This first step makes you feel you're kind of losing, you're dephasing, so you're flipping a phase, so you're creating destructive interference, and this basically that's like it just flips the effect into positive interference, um, and it has the effect that it's even more powerful, so to say. Oh, okay, I have to sleep on this, and I'll try to make another video where I try to maybe explain that in a cleaner way, in a cleaner way. But that might be it. So indeed, Mr. Craig, you actually, you're awesome. You're really awesome. That that is the trick. That that really makes it. Would be interesting to try to understand it at that low level as well, sort of Hadamard and and these. But now I look at the control Z. Oh, oh my God! Now I look at phase shifting completely differently. Now I look at phase shifting completely differently. Because it's not that you're changing something and you're losing it. You're just adding something to the mix that's creating that destructive interference effect. Oh, my mind just blew up right now. That's it. That's what dephasing is. That's what phasing does. Phasing is not just it. We're always adding stuff. That's my point. That's the point. We're always adding stuff. It just sometimes feels like it cancels out and it adds up. But that's the whole point of playing with waves. Nice. Okay, I probably should go sleep, but I'll. Oh, it's like 4:30 in the morning here, but it's basically this. This has been an eye opener. This has been a really big eye opener. That's actually a different. That's what's different in terms of thinking classically, and in the sense that those are here playing with the waves, and feels good. I hope I'm not total bullshit, but uh, that somehow makes sense. Somehow. But maybe I'm wrong, but that somehow makes sense.